just got done yesterday saying how, well, you know, a theory continues to be challenged and, you know, experiments are continually done to see if this theory is correct. And you're never really sure, okay? Theories can be changed. You know, and if you notice something, there was a step missing that you may have memorized about the scientific methods before. By the way, I've seen multiple versions of the scientific method over the course of my lifetime, and even over the course of the books nowadays, if you were to look at them. The fact is, I only had 4 steps. They're the bare minimum: observation, hypothesis, experiment, and theory. Some of them will say law. Theories that have been shown to be correct for a very long time have not been disproven. We tend to call them laws, like, you know, law of gravity. Let's just use that one as, because you don't really haven't had physics yet. But you know, I mean, Newton's laws, Newton's first law, second law, and all that stuff. We call those laws. In reality, we kind of take that. I took that away. I didn't do it myself. That book we used takes that away, because laws are changed all the time. It's unfortunate, but we're not right all the time. It'd be nice if we had the final word on all this, but we don't. So, like I showed you when I was talking about some of my examples, I can't open the box. I can never know if this is a paperclip. All right, I could do experiments on it. I could put it next to a magnet. Oh, it's magnetic like a paperclip. It sounds like a paperclip. It moves like a paperclip. It weighs the same amount as a paperclip, but I can't open the box, and I can't open the box for the universe either. I can't see an electron. I can't see these subatomic particles. I can only do experiments and see how they behave, and then make conclusions from that. And I'm pretty sure about my conclusions because I got a lot of evidence. All right. Well, having said all that, here I am giving you the first one. Now, we use the terminology anyway. We use Newton's laws, even though we know that some of these things can be changed. The first law is one that's been shown to be correct for a very long time. And it may surprise you that this is not as intuitive as it sounds. Some of you are probably thinking to yourself, when you read this, law of conservation of matter and energy, that, well, obviously, everybody knows that. It just says matter and energy can't be created or destroyed, but you can change one to the other. Okay? And what I told you yesterday about taking notes. Read the whole thing. Listen to the whole thing. Matter and energy can't be created or destroyed. Just changes form. Okay? Shouldn't be bobbing your head up and down 10 times for 10 words. And that's good. You're not. All right. Now, that sounds intuitive to all of us because we've grown up in a scientific age, and we all believe this. We all know this. Well, I wouldn't say we know it, but we all believe this. Can't make things out like magic. And so you think, well, people wouldn't believe this would be like, you know, the Druids or magicians or, you know, some alchemists or some people from the, you know, Middle Ages or the Dark Ages or even before that, prehistoric times, might have believed in this kind of stuff, that you could just get something out of nothing. We all know that's not correct. But really, you have to realize it wasn't that these people who lived maybe 100, 200, 300, 500, 600 years ago were stupid. It sure appears that I can destroy matter. Think about it. Some of you probably have a fireplace, right? And you stack wood outside your house, and you burn that wood all winter. Now, if you were to weigh how much that wood weighs before, and then after you burn it, weighed the ashes, you'd say, well, we destroyed a lot of matter there, okay? Or you might even think, well, we converted all that matter into energy if you're a scientific person. Neither of is correct. Neither of those things is correct, all right? Fact is, and I'll talk about this as part of my demo, the law was held true. But we'll talk about, with my little demonstration here, why that is. I'm going to do a little demonstration. All right, so let's do this. I think, hold on one second. Yeah. By the way, does anybody know, before I do my demo, does anybody know who, what the changing form between matter and energy, who came up with that? Matter and energy, how they're related. Energy, matter, E and M. What do you think? Einstein, yeah. Einstein said, yeah, E equals MC squared. Do you remember that? Okay, you've heard of that. He's the person who was able to realize, I mean, that's probably the most recent part of this. Before that, people realized that there was a conservation of matter and energy. You couldn't create or destroy it. But he was the one that came up with the idea that, hey, we can interconvert these things. Matter can be converted into energy and energy into matter, supposedly. You know, he's the one that came up with that. And the equation is E equals MC squared. I'm actually going to use that equation. I know you're going to, by next chapter, I'm sorry, by the third chapter, we'll be using that equation to do calculations with wavelengths and energy and electrons and orbitals. You're not, you know, you're actually going to do some pretty tough math here, all right? And some other equations harder than that. Obviously, that's not that hard. All right, let me show you a little demonstration of this law. Okay, I have here a. Whoops, I hit off. That was dumb. I have here a balance. I'm gonna probably not be able to. I'm gonna kind of just tilt this over to here so you can see that one over there. I want to make sure you can see it. It's not quite so easy to see. All right, and I'll show you. But that way I can show you my stuff here. Okay, you guys are going to have to use this balance on a regular basis. Okay, so there's your balance. All right, when you turn it on, you just press the on button. Now, I'm showing you how to use this for a reason. You're going to be using this by next week. All right, you're going to be doing things with it almost every lab we do. We're going to be using electronic balances. It's important you know how to use them. For example, if I wanted to weigh this is the first thing people do wrong. Nothing's happening. Oh, I kind of need to pull back a little bit. Nothing's happening. Why not? The lid is not up. Yeah. And it is amazing how people will do that. It will. Now, not all of these have a lid, by the way. Some of them they've broken off over the years. So that's why. If you move from one place to another, the previous one you had didn't have a lid. This one does. People just don't even pay attention. They put stuff on there. How come it doesn't weigh anything? It does. All right. You just have to lift the lid up. All right. There's also another neat thing about this. Oh, move that thing out of the way. There's also another neat thing about this. And let me move this back a little bit further so I can get a bit of a larger picture here. Come on, stop it. There you go. A little bit bigger picture there. Now, there's also a neat little feature on these that you may have seen if you're at a salad bar. All right, it doesn't weigh your dish. It just weighs the salad that's on it, or it's supposed to do that. So if I put something on there, all right, like let's take one of these guys, and I wanted to know how much this marble weighed, right? But I didn't. If I put that on, it's going to roll off. So I could put this on first, right? Now that right there is my little container. Usually you're not going to use a film canister since nobody uses film anymore. We're using beakers and other stuff and little weighing boats. If I hit this button right here, which says 0 on it, look what it does. Uh-oh, doesn't weigh anything anymore. Now, whatever I put in there, I'm only weighing that. You see? Okay, and that's what you'll have to do many times. Because I don't care how much the beaker weighs. I don't care how much the test tube weighs. I care how much the stuff inside of it weighs. All right, I'm looking for its mass. And I keep saying weigh, but really I mean mass. That's what you're getting on the scale. All right, so let's do a little experiment here. Let's do a little demonstration. I'm going to take this. Well, let me get in front of the camera here. You can probably see it. Yeah, okay, good. I'm going to take this soda bottle, and I'm going to add some baking soda and vinegar. This is about as easy as a demo as it gets. We're going to do a lot better demos than this, even by tomorrow. Or actually, I don't know about tomorrow. Tomorrow we have a double. We might get to it tomorrow for your class. The other class we won't. And I'm going to weigh how much I got in this. So let's put it on a scale first. All right, there's my scale. I don't want to weigh the container, so I just want to weigh that. So I'll hit the 0 button. All right, and now when I add some baking soda to it, I can tell how much I have. Right? I'll just put that baking soda in there, and 1.59, a little bit more. I want to get around 2 grams, so put a little bit more in. Oh, I forgot to mention to you. You know what this is? This is a spatula. Okay, that's what you don't want to touch chemicals. Obviously, baking soda is not going to kill anybody. Well, I guess it could, but it can kill. I believe, I don't know how true this is, seagulls. You know what? Seagulls can't burp. This is what I heard. This is maybe an internet legend. So if you toss, into the air like bread, seagulls will eat it on the beach. They eat everything. Well, if you toss them into the air, what do you call it? Alka-Seltzers? They explode. They die. It's a bad thing to do. I'm not saying you should do this because they can't get rid of the gas fast enough. Like if they eat the thing, and it's actually kills them. It's terrible, isn't it? I don't know why I heard that. It's probably an internet rumor. It's one of those things, but it's not really important. All right. What I wanted about 2 grams. Okay, so I got 2.02 grams. That's how much that weighs. But I'm not going to write that down because I also want to weigh beforehand. I want to weigh how much this vinegar weighs too. So I'm going to put it into. If I just add it in there, it's going to start reacting right away. It reacts. So what I'm going to do is put it into a little test tube first. Let me make sure I can fit that one in there. I can. So I'm going to add this into a test tube. You watching? Taking a little bit of vinegar here. And hopefully I won't spill it when I put it in here. And I'll weigh it again. Yeah, turn it down sideways there. Whoop. Hopefully I didn't spill. Put it on here again. And let's write this mass down. Okay? Actually, I'll even put the lid on. No, I won't put the lid. 32.14. 32.14. I'm going to write that down because it says it right there. 32.13, 32.14. Okay. Now, hope that wasn't a permanent marker. No, good. Sometimes you just pick things up and you're right, and then that's not good. All right, now what's going to happen when I turn this guy over? When I mix these guys together? You've seen this before. It's fizzing. You can hear it fizz. You can see it fizz. We're not surprised by that. You've been doing this experiment since you were a little kid. Okay? Isn't that cool? Okay. As much fun as that is, let's go back. So you can't see it on people at home. You folks at home can't see. Law of conservation of matter and energy said, but I think you all know, matter and energy can't be created or destroyed. So just because I carried out a reaction, right, that doesn't mean I'm going to have any change. So when I put this back on here, what should it weigh? 32.14, right? I just violated the first law I ever gave you. I have done something that no one's ever done before. Okay, can anyone want to tell me what the flaw was in my experiment? Anybody know? They should weigh the same. They should absolutely. So I know what some people are going to say. Well, maybe it was converted into energy. No. The amount of energy, if that many grams, that much, it went down to 31 point something. If that much mass had been converted into energy, you'd all be dead right now because that would be a lot of energy. It would have killed you. Okay, it would have blown up in your face. No, it wasn't that. It wasn't that at all. Anybody know what I did wrong? What did I do wrong?
You didn't zero the test tube.
No. I remember I did weigh it with the test tube still in there. You're right that I didn't zero it, but I didn't have to because the test tube's still in there. So I'm still weighing the test tube. That's good. That's good. I'm glad you picked that up. That I didn't have to zero. I could have, but I didn't have to zero it in this case because it's still in there. All right. I'm just looking for the total change in mass. Now there's something else I did that you don't realize. It has to do with that example I was telling you about with your fireplace. I told you that those logs beforehand weighed more than those ashes at the end of the winter. How often do you change how often do you rip out those ashes from your fireplace? Once a week, right? Maybe. And they don't weigh all the amount that those logs weighed. Where'd all that mass go? Same place it went here. Where? Up your chimney. Let's try doing this again with the lid on. You see? What was produced here? You all saw the fizzing, right? What was produced? A gas. Turns out, what gas was it? Anybody know? You should know. It's like the most famous one. This one Al Gore talks about all the time. You don't even know who Al Gore is. But global warming. Climate change. What gas? Carbon dioxide. Very good. Okay. So that's what was produced. So don't tell Al Gore we're making more carbon dioxide because he'll get mad at me. All right. Let's try the same thing again. All right. Only this time we'll put the lid on. Now, notice something about, these are all sources of error that you have to watch out for. I don't really care that there's water inside this container, but I do care that there's water on the outside. Because what's going to happen if I have water on the outside when I weigh and put this down, right? What's going to happen? Well, when I weigh this one time, maybe I'll leave a little water on the scale. Next time I'll put it down, and if you look here next to it, you know, if I have little drops of water along there, if I don't dry this off well, that mass is going to change. You say, well, so what? It's just a little bit of water. We're talking about a very small mass here that we're losing. So I've got to make sure that I dry this off really well, especially on the outside. The inside's not as big of a deal because I'm going to weigh it, kind of like that test tube's not as big of a deal because I'm going to weigh it before and after, so it's still there. That water that's in here is still here. But the water that's here is coming off of my hands, it's coming off of the table, it's coming off of the scale. That water, can't have it there. So you always make sure the outsides of your beakers or containers of whatever kind are always dried off well. Let's do the same experiment, okay? Get rid of a little bit more of that water. Okay, 2 grams. About. Oh, but it's going to be a different zeroing this time, right? So I'll zero it again. Why is it going to be a little bit different? Why is it not zeroed anymore? There's water inside of it. Okay? Now I'll put about 2 grams in here again. It doesn't have to be exactly 2, but around 2 grams. Let's see what we got. Ah, wow. I'm the estimator. Okay. 2.03. Now, I'm not going to write that down yet because I still have to do the vinegar. By the way, does anybody remember which cap was the vinegar? They look like identical, don't they? Oh boy. Well, hopefully I put the right one on because I want a tight seal on here. Okay. Same thing. Take a test tube. Same test tube, basically. And we'll fill it up with vinegar. Okay. Wipe off the outside. Put this guy in here. And let's see. Slide him in without spilling it, hopefully. And then we're going to put the lid on, too. I put the lid on because I don't want anything escaping this time. I hope it's the right lid. Now, put this on here. And I weigh this. And notice this is slightly different because I've got water inside of there. I've also got a different amount of vinegar. I didn't measure that out. And I put the cap on. So it's not exactly 32.14 again. But that's not important. What's important is, will it change? So this is now 34.84. Let's see how close we get to 34.84 this time. Last time we lost almost a whole gram, I believe. This time, let's see what happens. You ready? We'll do the same thing. We tilt them upside down. We see them fizzing again. We can even hear it through the bottle. Move it around. We wait till it's done. And then we put it back on the scale. And this time, it basically weighs the same. Now, you'll notice it's not that little number, 8.81, 0.84. It didn't lose up. Last time it was down to like 33 point something. I mean, it lost like a whole gram. That little bit of change there, I mean, there could be leaks in the top. There could be water, like I said. You don't get all of it off of there. Matter of fact, sometimes the amount of water is so important that we'll actually have to heat something multiple times. It's called heating to dryness. Until we're sure that all the water is out of it. We'll heat it like 2 or 3 times and keep weighing it until there's no longer a change. All right, so I have, let's turn our thing back over here. I have then, confirmed, I guess is a good enough word, the law of conservation of matter and energy. I have not violated it. Turns out that when I do a reaction, I don't create or destroy energy, or I don't create or destroy matter. It doesn't happen, all right, in any reaction. But again, you shouldn't consider people who did think that idiots, because it sure looks like we destroy matter all the time when we blow things up and when we burn things. But in reality, it's just being changed. And sometimes it's being changed to a gas. And that gas goes off into the air, and so you don't see it. But if, believe it or not, if you were to collect all of the stuff that went up your chimney, it's hard to believe. If you were to collect all that stuff that went up the chimney, all the gases, everything, and the ashes that are left there in your fireplace, they would weigh the same as that wood pile out there at the beginning of your winter. Hard to believe, but it's true. All right. Now you say, well, some of it was converted to energy. Yeah, but so little. You have no idea. When we get to the nuclear chapter, you're going to find out that the amount of energy you're talking about, the amount of mass that you lose when it's converted to energy is so small that it's virtually negligible. You can't really measure it, except in a nuclear reaction. You can see a real change. But other than that, you're not going to see it in an ordinary chemical reaction. You're just not going to be able to measure that. All right, so you learned a couple of things in this first demo. We confirmed the law of conservation of matter and energy. We also learned how to use this electronic balance. Hope you remember that. What's this called again? Spatula. You're going to have to know how to use this equipment and know the names of all this. Your first safety lab test is going to be, quiz is going to be a safety lab. You're going to have to identify all of the equipment in your drawers back there. We'll do that probably starting next week. If not, it'll be early the week after. We have, when's Labor Day? We don't have Labor Day next weekend. It's the following, right? So we don't have the following one now. So we have a full week next week. We'll probably get to the lab stuff by next week. All right. Now remember, I said this, I think yesterday. I said how biology has so many more notes than chemistry, right? And here's why. I'm not just giving you notes to be memorized. I'm going to almost always do stuff with them, okay? And yesterday we got one board of notes, and it took me the whole period. Today, we've taken over half the period on one sentence of notes, okay? So I don't necessarily give you anywhere near as much information, but I'm going to try to explain it to you better and ask you harder questions on it. All right, next thing. Homework up there, you can write that on the board, or write that down in your not on your notes. Remember, 2 separate sections, and we're not done. I have more notes to give you. But write that down in a separate section. If you want to, you can just start at the back of your notebook and write that down there. You go work backwards with the homework and forwards with the notes. I don't care, as long as I have all of them separate. You know, when you hand them in, you're only handing in the homework. So write that down real quickly. I'm going to put it on the board over here at the end of the period, but hurry up and write it down. Because I got to do some more notes here today. We don't have much time, but kind of wasted a lot getting this whole thing set up because I didn't have my projector. All right. Y'all got that? I hope. Now, you know, we're talking about matter and energy, so I'm going to spend a little bit of time on energy. And I want to go over energy with you quickly here today. All right? What is energy? How many of you guys are in physics? Okay, quite a bit of you. You're going to do a lot more with energy in physics than you do here. And the way you look at physics, the way physics looks at energy, I should say, is different than the way I look at it. Okay? It's much different. Let me show you. We call energy, Schrader will use the same one in physics class, the definition is the ability to do work or transfer heat. Schrader in physics will concentrate on that word right there, work. Anybody had physics already in here? Anyone? No? Okay. Well, you're going to learn about work a lot in his class. Okay? And work is basically just applying a force through a distance. So I'm doing work if I push this scale somewhere because I've applied a force and I've moved it through a distance. But Mr. Schrader would say, if I push on this wall, if I push on this projector for all day long or for an hour, I didn't do any work because the projector didn't move. So there was no work done. But we know we did because you're going to get hot, you're going to get tired, your muscles are going to get sore. You know, there was work done. So chemistry looks at transfer of heat. They both are different ways of measuring energy. Chemistry concentrates on that. And let me show you with an example of what I mean by that. When I talk about the 2 different kinds. You've all heard of these 2. By the way, a lot of this first chapter is going to be terms you've heard of before. Who has not ever heard the term potential and kinetic energy, right? You've all heard that in past classes, correct? I'm not, assuming facts that are not in evidence. What do we know potential energy is? Stored energy? Energy of, what's the word? Begins with a P. Nobody? Position, right? Like what has more potential energy, guys, right? If I pick this up off the ground, it has more potential energy, right? Because I can drop it and it will hit harder, right? And it has less potential energy at a lower height. That's how potential energy was always explained to you. It's stored energy. The energy a body possesses by virtue of its position. But I'm going to add something to that, something that you did not see before. That's what a lot of chemistry is going to be about in this first early chapters. You're going to take a familiar concept, and we're going to expand on it, do more with it. That expansion involves one word, composition. And I'm going to have a little demonstration to illustrate both of these guys for you. Schrader, in physics class, only concerned about how high this is. So, for example, he's concerned about the height and the mass of a beaker. I couldn't care less how high you hold the beaker up while you're mixing it up. What are you going to probably be measuring? You're going to be measuring the temperature change. You're going to be measuring how hot it got. That's another form of energy. Okay? So potential energy is, here, good example. If I have a glass of water that weighs 20 grams, and I have a glass of juice that weighs 20 grams, and I hold them at the same height, according to physics, they have exactly the same potential energy. But if I drink the water, and if I drink the juice, which one has more energy in it for me? Juice, right? It has sugar in it, has other things in it that I can pulp, it has other things in it that I can digest and get energy from. All right, so kinetic energy, again, you've always been told, is the energy of motion. The energy of motion. And that's true. I'm not saying what physics says is wrong or what you learned in middle school is wrong. What I'm doing is expanding on that. All right. In fact, it is the energy of motion, or a body possesses while transferring heat. So either one is kinetic energy. Heat is the movement of molecules. Molecules are moving around faster when they're hotter. And so although you can't see it, although Schrader can't see me pushing this projector anywhere, it's not noticeable to a physics person. It's noticeable to my muscles. It's noticeable to my body temperature. I'm going to get warmer, and I am moving things around. All right. Now I have a nice little example of that here today. Okay, and I have just enough time. This is 33. It's over, right? Okay, check this out. Y'all got that copy? You should, because you should be reading, writing sloppy. That's the other thing I didn't mention again today. Okay, check this out. I'm going to tell you a little fairy story. You ready? My little fairy story. I made this up myself. I really did. I found all these little pictures online, and I made this up. All right, and of course, like every fairy story, you have to have a princess. Who's that?
Princess Fiona.
Yeah, turn the light off. Maybe you can see. I don't know if you can see it better or worse with the light off. Yeah, I think you can see it better that way. Can you see it better that way? Okay, that's Princess Fiona, right? She's stuck in the castle, right? Okay, a little sexist here. That's all right. Fairy stories generally are. So we need a dragon. There was a dragon in that one. This isn't the exact same story as Shrek, but that's a pretty nasty dragon. You see that? I made him. I didn't really make him, but he's an animated gift. You see what he did there? All right. So Princess Fiona is stuck in the castle. Now, let's just say that this is Mr. Schrader. Okay, that's Schrader. Notice my very similar rendition to. And do you remember who that guy was from the Disney movies?
He was in Shrek.
Yeah, he was in Shrek, and he was Prince Charming, wasn't he? I believe, but he was a jerk, right? Okay, Schrader's a jerk too. I'm just saying. He's not. We're good friends. But Mr. Schrader, he's a chump though, because here's the deal: at the top of this castle, there's a bowling alley. Okay, don't ask, but there are, and there's also the armory. Now, Mr. Schrader, being a physics guy, says, well, these bowling balls weigh the same amount of these bombs, right? So he's going to throw, that doesn't really, oh, how about that? He throws them at the, that was pretty, it was like 3D. It was coming out at you. He throws the bowling ball, hey, whatever, just throws the bowling balls at it because they weigh the same and therefore they have exactly the same potential energy according to physics, chump that he is. Well, that just ticks off the dragon. He gets even angrier and angrier, and eventually, Mr. Schrader goes away somehow or other. Probably gets eaten by the dragon after throwing all the bowling balls at him. All right, well, here comes now our hero. That's me. Ta-da! Here I am. Who's that?
Prince Eric.
Prince? Is that? No, I don't. Is it? That's from Cinderella.
Yeah.
What's his name? I think that's also Prince Charming, isn't he? He's also. I'm the real Prince. He was the poser. I'm the real Prince Charming. Okay, this is me. Now, I know if I light these up first and throw them at, and the bombs, not the bowling balls, and I do that, I have a better chance of defeating the dragon and saving Princess Fiona. Watch. Ooh, you see that? I blew them up. I did all that. Isn't that nice? Very, very realistic, too, as you can see. And, of course, we lived happily ever after. Kind of mix my metaphors here. I use my 20 different Disney movies. Who are they? That's Sleeping Beauty or no? Snow White, right, Snow White. So there's another Prince Charming, right? There's a third Prince Charming. I just watched Maleficent. You see that one yet? Remember that was like, okay, anyway. All right, so yeah. But you get the point. Schrader physics only concerned with how high the mass and the movement of it. We are concerned with what they're made of. A bomb contains more energy in it, in the molecules that make it up, than a bowling ball. Water contains less energy than juice, right? Than Gatorade. Okay, you get the stuff that's in the Gatorade, the sugar and the other stuff that's in the Gatorade, is got more energy in its bonds than it has, even though they weigh the same amount at the same height. If I drop them, they're going to make the same splash. All right, but that's not what we're looking at in chemistry. We're looking at what its composition is, like the definition said, position or composition. Okay, hit that light for me. Turn it back on, the back one, please. And